Well, hello and welcome. In this video, I'll be covering section 4.2, which is over graphing polynomial functions. My goal for you by the end of the video is to be able to graph polynomial functions, as well as be able to use the intermediate value theorem to determine whether a function has a real zero between two given real numbers. So some things that we need to take into account when it comes to actually providing graphs or creating graphs of polynomial functions is if we first can identify what the degree is. In this case, we'll go ahead and just call it the value n. Our function, when it comes to the graph of it, will have at most n of those real zeros, in other words, x-intercepts. And then we'll have at most n take away 1 turning points. So if the degree was 5, it would have at most 4 turning points. Now turning points, as far as what can we relate that to from our past, those were things that we called relative maxima or relative minima, which is essentially any time our function switches from increasing to decreasing or decreasing to increasing, either way. So again, all high points and low points really are considered turning points on a graph for a polynomial function. So as far as how do we create a graph of an entire polynomial function, we kind of combine all of the things that were talked about in the previous lesson along with what I just presented there, as far as knowing how many high points or low points at most we could have, as well as how many x-intercepts we could have. Being able to take into account multiplicities as well as a y-intercept is also something we can take into advantage. And then the very last thing, or actually really should be the first thing we do, is determine what the arrows are going to do. In other words, the end behavior. So remember, the end behavior was based upon what is the leading term test. In other words, does the degree happen to be an even number or an odd number, as well as is the coefficient on that positive or negative. And we had those 4 different cases where either both arrows pointed up, or they both pointed down, or they pointed opposite directions like a positive slope, or potentially they pointed opposite directions like a negative slope. Now when it comes to finding zeros, remember that usually is going to involve some form of factoring. Any of those solutions that come back as real, we then can say that would be an x-intercept, so it would give me a point that I could actually plot. Anything that comes back imaginary really won't help when it comes to the actual creating of a graph of a function. Now what we'll do is go ahead and plot those x-intercepts, kind of like we did with a few examples on the last, I guess, page of notes, at least those that worked with me. And we basically will use those to kind of divide our x-axis into smaller intervals and then just kind of test some values in between. So you can kind of think of that as creating a little t-chart to kind of fill in the blank in between the x-intercepts to determine potentially how high or how low a graph might go. Another thing that can be helpful is just plugging 0 into the function. Remember, plugging 0 in should just give us a y-intercept, so that would give us yet another point that we could plot. And really, the more points we have, the more accurate our graph would be. Now, if it's necessary, go ahead and plug in even more values outside of the shape just to kind of give us an idea of what the generic shape of the graph would be. And then actually just start connecting the dots, making sure that we're accounting for what the end behavior was at the very beginning. So our goal is essentially to start with our arrows and just figure out how I connect them in the middle. Now, as far as how you can kind of check your answer at the end, is you could take whatever the degree is. So again, if the degree is n, that would be the most x-intercepts I should have. So if I had somehow, some way graphed 5 x-intercepts, but my degree was only a 3, then obviously I must have done something wrong when it came to either the factoring or just maybe I plotted way too many numbers or just plugging into the function. Maybe I got some values that didn't really make sense because maybe you typed in something like -2 squared and you actually got -4 when it should have been +4. So those are little things that you can do to kind of just check, does my graph even make sense? The other thing we can take into account is how many turning points we should have. Again, that would be 1 less than whatever the degree is. So again, if the degree was 4, I would go ahead and say that, well, at most I should see 3 turning points or a combination of maximums and minimums that would total up to equal 3. Now, multiplicities can also help with just what's going to happen as I pass through some of those x-intercepts. Remember, even multiplicities will just touch the x-axis, whereas odd multiplicities will actually cross over. And as you get into like powers of 3 and 5 and 7 and so on and so forth, it actually would go through a graph. If I were to try and sketch, so let's say we had a 0 right there that had a multiplicity of either a 3 or a 5 or a 7, it would kind of go through and curve in a way as it goes through the actual x-intercept. But because it would be an odd number, with it being either a 3 or 5 or a 7, I know it physically has to cross at that particular value. And again, the very last thing that we can do, which some of you have access to, is just type the graph into, or type whatever the function is into a graphing calculator, or potentially if you're at home you could type it into Desmos if you didn't have a graphing calculator, and just at least look at what the true shape should be and compare it with your results. Alright, so let's go ahead and try out an example here. Obviously this is a little bit more intense function than we probably have ever really been required to graph, but let's just break it down into the small parts that we've encountered so far. So as far as identifying some of the key parts, it looks like the degree for this one is going to be a 4, because that's the highest power I see. Since that's an even number, I know that my arrows should point the same direction. And since this has a leading coefficient that's -2, so if I just maybe list out some of these things, the leading coefficient is -2, so my end behavior is going to be the arrows are going to both point down. As far as how can I get some of my zeros, well, the zeros in this case would be probably best suited if I were to maybe factor this out. So it looks like I can factor an x cubed out of both terms, and that would leave me a -2x plus 3. And so if I set that equal to 0, the zeros that I get are going to be 0, as well as the second one I would subtract 3 to move it over, and then divide by a -2. So I'd have a negative divided by a negative, which would come back positive, and 3 was the first thing I moved, then divided by 2, so 3 halves. Now each of those at the same time I can identify what the multiplicity is. For 0, it had a power of 3 on that x in front, so that will have a multiplicity of 3, whereas the multiplicity on the factor where the 3 halves came from, there was no power in this area, so I know that its multiplicity technically then would be 1. So what does that mean is happening at each of these? Well, because those are both odd numbers, I know it actually is physically going to cross over the x-axis at both of these values. It's just going to be, when it passes through 0, it's going to be more of kind of a curvature. It could be either going up like that, or it might actually be coming down the page. But it's going to have some form of curvature as I pass through that 0. Another thing I could identify, in this case we already, in I guess some way, shape, or form kind of got this, but we could also get our y-intercept explicitly written out. Our y-intercept in this case is just going to be what happens when I plug 0 in. Well, when I plug 0 in, it truly was a 0, so I'd get 0. So this will have a y-intercept and an x-intercept that actually is at the origin. Now as far as what else could I potentially do, well, I know I'm going to have at most 3 turning points because the degree was 4. 1 less than that would be 3, so there should be at most 3 turning points when it comes down to it. And then maybe let's just fill in the blank in between some of the areas that we have. So if I know that 0 is 1, and I know that 3 halves is another, which would be halfway between 1 and 2, seems like maybe some good numbers to maybe plug into the function would be like -1, maybe even +1, and maybe even +2. That seems like maybe it will give me enough info to be able to actually go through and plot some of these values. So if we go ahead and plug in something like -1, the even power will make that turn into +1, so that would really be like -2, and then -1 cubed would make that a -3. A -2 and a -3 will give me a -5. A +1 when I plug it in, that really should just keep the 2 coefficients, so -2 plus 3, that would give me +1. And then 2 is going to be a little bit tougher to do as far as mental math is concerned, but it would be a -2 times 16, and then plus a 3 times 2 cubed, which would be an 8. So -32 plus 24, that would come back as a -8, which I don't think is actually going to fit on my grid over here. So I know that at +2, it's going to be way down here at -8, so that kind of lets me know that my arrow on the right, that I knew was again pointing down from our leading coefficient test, is going to be right about there. 1, 1, I can plot that point. And then -1, -5, that would be down here. So it seems like this arrow is also going to be relatively close to the y-axis. So now if I were to just kind of go through. The multiplicity again here at 0 was a 3, so it's going to kind of curve through. Then it will go up to maybe that as a high point, and then actually go straight through with a multiplicity of 1 at 3/2. And there we've kind of sketched a really rough estimate of what the graph truly would look like. And again, you could bring a graphing calculator or Desmos into the problem and just kind of verify, did I at least have something that was close? Because again, we're just really doing a rough sketch of these things, but we should have a few key points when it comes to actually plotting the graph. So just kind of keep in mind that I'm going to be looking for some of those key points, or looking for like a table like I did over here with the XY T chart that kind of shows what some of the points were that you were using as references when it came to creating that sketch. All right, move on to another example just to try and hammer this point home. So with this, let's go ahead and first identify our end behavior. So start with what is the highest degree. Well, with this one being in factored form, I have to kind of think what would be the highest powered term from each product. Well, in this case, it's just an x times another x times another x times another x. Well, x times x times x times x, that's really x to the 4th. So our leading term would just be, and it looks like all of the coefficients were +1, so my leading term would be just a plain x to the 4th. So since that has an even degree with a positive leading coefficient, that means the two arrows in this case are going to both point up. I just need to figure out what's going to happen in the middle. And let's see, is there anything else I can identify from the leading term? Well, since it's got a degree of 4, may as well identify that. Degree was 4, which means turning points can be at most 3. Doesn't mean it has to have 3 turning points, just that's the most I could have. And it also means that I can have at most 4 x-intercepts. So let's go ahead and find those zeros and see how many of them potentially could be x-intercepts. In this case, I would set each parenthesis equal to 0, so my zeros are going to be, it looks like from the very front, that would just be 0 itself. From the second one, I would add 1 over, so +1. The third parenthesis, I would subtract 3, so -3. And the last one, I would have to subtract 2 to isolate x, so a -2. And all of those were singular. I didn't ever have any of them repeat, so all of them have multiplicities of 1, which then means it just goes straight through at each of those and actually physically crosses over the x-axis. Now, as far as a y-intercept is concerned, we could again identify what that is explicitly just by plugging 0 in, but since 0 actually was one of the zeros, my y-intercept once again is going to be the origin. So let's go ahead and see if we can maybe put a little bit more, actually let's get some more points here. So if I were to maybe just give myself a visual for where some of these points are, let's at least put them on the grid. So -3, -2, 0, and +1. Some numbers that maybe will be helpful as far as like determining how high or how low it goes in between these would be like -1 is a pretty obvious one for me. And then the other ones would be something that would be decimals, which I could use a calculator to kind of approximate those. So maybe something like -2.5 in between the -2 and -3. And let's see, maybe 0.5 in between 0 and 1. And then maybe let's just do 1 on the outside of each of those. So maybe -4 and +3. So let's see, when I plug -1 in, it looks like I get a y value of 4. When I plug -2.5 in, it looks like I'm going to get a decimal that's about -2.2-ish. Plug in 0.5, gives me a value of about -2.2-ish as well. And let's just see if the other ones even fit. At 4 or -4, it's all the way up at 40, so I didn't really have to worry about that one. And let's see, at 3, let's see what we get. 180, so that's going up really darn fast. So those ones weren't really helpful, but the other 3 at least give me some idea of some points that I could plot. So at -1, it was up at +4. At -2.5, it was down here at -2.2-ish, so somewhere right about there. And at 0.5, it was also down at about -2.2-ish. We established at the very beginning that I had arrows that were going to point the same direction, and specifically both up, because it was an even degree with a positive coefficient. And each of these x-intercepts, because their multiplicities were 1, mean I get to just pass through them. So really now it's just try and make this a nice smooth curve that passes through all of these points. So it kind of creates a little bit of a W shape for this one. Now, as far as double checking here, it looks like I had 1, 2, 3 total turning points, 2 minimums and 1 maximum, so that at least confirms what I thought could have happened. And I have at most 4 x-intercepts, which match the degrees, so as far as the logic behind what my graph looks like, it seems good. But once again, we could type it into maybe Desmos or a graphing calculator and just double check if our graph actually was reasonable. And the last concept we'll cover in this section. So as you can see, this section really is just kind of combining everything thus far that we've talked about, just introducing the concept of maximum number of turning points as well as maximum number of x-intercepts. But we also have this thing called the intermediate value theorem that can kind of help us identify whether there should be a real zero that falls between the values, even if it's not something that's nice and perfect when it comes to being able to factor. So for any polynomial function that has real coefficients, in other words, I don't see any i's on any of them, which polynomial functions cannot have i's in front anyway, what we would have is if I guess, have 2 different numbers, so notice it's saying if we have a and b and they just don't equal each other, if I plug them into the function, remember plugging them in would give me y values back. If I happen to get 2 opposite valued numbers, meaning like one comes back positive, the other comes back negative, because a polynomial is continuous, if I ever have to switch from a negative to a positive or vice versa, graphically I would have to cross over the x-axis. So that basically means from this intermediate value theorem that if I have 2 numbers that when I plug in give me opposite signs, somewhere in between there had to be a real zero, because again, real zeros are the actual x-intercepts. So really it's kind of a common sense thing. In order to go from below the x-axis to above the x-axis, I have to cross it. So the intermediate value theorem is just kind of confirming that that logic actually is sound, because polynomials have to be smooth and continuous. So if I ever notice that I get 2 that are both positive or 2 that are both negative when I plug in numbers, then the intermediate value theorem really is not something I can apply, because it does have to be perfectly opposite. Or I guess not perfectly opposite, but you do have to have 1 positive and 1 negative. So the types of questions that you'll have with this will just kind of give you a couple of numbers and go, will there be a real zero in between these values? And ultimately it just comes down to if you get 2 different values that are opposite, then you would say yes, there has to be a zero in between. If you get 2 that are the same sign, meaning both values come back positive or both values come back negative, then you just say there is no guarantee that there's a real zero. So to provide just an example or 2, I guess, of what this would be, I'll use the same function both times. So x cubed plus x squared minus 6x is the function we're plugging into. But notice this has kind of 2 parts where it just says, if you use the intermediate value theorem, can we guarantee that there's a real zero in between these values that they've provided? So for part A, I would essentially just figure out what is f of negative 4. And then I'll also need to figure out what is f of negative 2. And so if I go ahead and type that in relatively quick, I'd end up with a negative 4 being cubed, then plus a negative 4 squared, which will come back positive 16, and then minus a 6 times a negative 4, and that one came back as negative 24. But do the same thing here with negative 2. Negative 2, if I cube it, would give me a negative 8 plus a negative 2 squared, so plus 4. And then minus 6 times negative 2 would become a plus 12. That came back positive 8. So since one came back negative, the other came back positive, the in between negative 4 and negative 2, yes, there would need to be a real zero. So a real zero exists in between there somewhere. Notice this isn't really necessarily helping us identify the exact value of that, but I could start kind of closing that interval. If I just tested -4 and -2, I could maybe move in a little bit and maybe try like -3 and -1 and just slowly enter, I guess, closer and closer and closer to each other, eventually maybe even bring in decimals in, and just looking for sign changes where one's still positive and the other is still negative. If I ever get two back-to-back that are positive or two that are back-to-back negative, then at that point maybe I went the wrong direction and just try a different decimal. If I go ahead and try the same thing with part B wants me to test between -1 and +3, so let's go with f of -1 would be a -1 plus 1, which is 0, and then minus 6 times -1, so plus 6, so that would come back +6. If I plug in 3, that would give me 27 plus 9 more, which would take me up to, let's see, what was that, 27 plus 9 more. So that would take me up to 36, and then take away 6 times 3, so take away 18. That would leave me with 18. Both of those came back as positive results, so in between these two values, there is no guaranteed, at least, real zero. So again, the whole point of intermediate value theorem is just plugging in numbers, looking at the results that I get, and if I have one positive and one negative, doesn't matter which one is which, as long as I have one of each, then that means somewhere in between those two numbers that you've plugged in, there has to be a real zero. So anyway, if you have questions on any of these, I guess, problems in your practice as you encounter them, just don't be shy to reach out and ask, and we'll do whatever we can to help. As always, I appreciate you taking the time watching the video, and we'll catch you next time.